In this video, I'll be discussing the first part of descriptive statistics, which is about tabular and graphical methods or visual ways in order for us to describe datasets. Now, we start first by discussing how to graphically summarize qualitative data. Between qualitative and quantitative data, it's usually easier to graphically summarize qualitative data because the possible values for the qualitative variable is usually limited. In this example, we have the qualitative variable Jeep model, which has 4 possible values only. So, since there are 4 distinct values for the qualitative variable, we can easily summarize this by getting the frequency for each value, and we call that a frequency distribution. So from the term itself, this frequency distribution shows us all the possible values of the qualitative variable and their respective frequencies. So in this frequency distribution, this was based on a data set of 251 jeepneys wherein the model was specified. So if you count all the jeepneys with the model commander in that data set, you'll get a frequency of 71, for granite 70, and so on. So this is the simplest and the most common way to summarize qualitative data. And from this frequency distribution, we can make a lot of conclusions like Liberty had the highest sales, while Wrangler had the least sales, while Commander and Grand almost had similar sales for that year. Now, aside from the actual frequencies of each value, we can also compute for relative or percent frequencies. So we can add these two columns to the frequency distribution. So for the same example, we can compute for those by just getting the proportion of each class to the entire dataset. So in the dataset earlier, we've seen that the frequency for Commander is 71 and the total for all the 4 classes was 251. So we can compute for the relative frequency by just getting the ratio. That's 71 over 251 or 0.2829. Now we do the same process for all the other values and we will get the following relative frequencies. And if you get the sum of all these relative frequencies, that should always be equal to 1. Now to compute for the percent frequency, we follow a similar process, but we just convert this to percentage. So we multiply this by 100 and add the percent sign and we'll get the percent frequency. And now if you get the sum of all the percent frequencies, that will always be 100%. So both of these values are representing the same proportion of the value of that class relative to the entire data set. They're just presented in different forms. One is in decimal format and one is a percentage. Now, this is a common way of visualizing the frequency distribution. So here, the emphasis is on the frequency of each value of the qualitative variable. As such, we can use a bar chart. So in a bar chart, either horizontal or a vertical bar chart, we put the levels or the values of the qualitative variable on one side, on one axis, and then we put the frequency on another axis. So in this example, the values of the qualitative variable are put in the x-axis, while the frequencies are put on the y-axis. And here, if you look at the values of the qualitative variable, we can see that it's arranged in alphabetical order. And we arrange it alphabetically because the jeepney model, this is a qualitative variable, has a nominal scale of measurement. As such, there is no ranking among the values, so we just arrange it alphabetically. Unlike if you have a qualitative variable which follows an ordinal scale, for example, Latin honors, it makes more sense to arrange it according to the order of the values instead of arranging it alphabetically. Now, there are other ways to improve or to revise the bar chart, you can have different ways of presenting this. In Microsoft Office, there are various options that you can choose from in order to make some revisions. You can add other aspects to the chart, or you can also remove some other aspects. But in general, this is what we call a bar chart. Now, this is an example of a chart that is used to emphasize proportions. This is a pie chart, so you have a circle that is divided into different slices, where each slice represents one value of the qualitative variable. So this is using the same dataset that was presented earlier. So we have 4 slices for the 4 models, and you can see here what the colors of each slice represent. And again, this is just one way of creating a pie chart. There are various ways of creating pie charts. There are various styles for this, and we choose the styles based on our goal. And we will discuss in a while how to select the most appropriate style in creating your pie charts. Now we move to graphically summarizing quantitative data, which is quite more complicated as compared to graphically summarizing qualitative data. First, the added complication is due to the larger number of possible values for the quantitative variable. Unlike qualitative variables, where the possible values are usually limited, as shown in the example earlier, there were only 4 possible values. For most quantitative variables, there are more possible values. For example, if your quantitative variable is age, we know that there are various values for age. Therefore, it might not be ideal to get the frequencies for each specific values of the age of the variable age. As such, one way to make it more to make it easier to visualize is to group the measurements into classes or into intervals and get the frequencies for each interval instead of getting the frequencies for each value of the quantitative variable. Now, there are 2 ways for us to categorize or to form the intervals of the quantitative variable. First is through predetermined classes. So some quantitative variables have standard ways of being categorized, and we just have to cite it based on we just have to cite what other studies have used in categorizing or making intervals for that quantitative variable. For example, we have here a way to categorize or to form intervals for the quantitative variable annual household income. So here we have 1.3 million and above, 650,000 to 1.3 million, and so on. So these intervals do not have the same width. Some intervals are shorter as compared to others, but this is a standard or a predetermined way of categorizing the values, so we can just get the frequencies of the values that fall within each interval, unlike getting the frequencies for each value of the annual household income. Another common example is the final grades. So as we know, final grades can be between 0 to 100, and there are predetermined classes or intervals for the final grade. So for an A, that's between 92 and 100. For B+, that's between 88 and 92, and so on. So similar to the previous example, the widths of the intervals are not equal, but this is already predetermined, this is standardized, this is well known and accepted by many, so we'll just have to follow it and cite it properly. But for some other variables, there are no known ways of being categorized, or there are no standardized way of categorizing or forming intervals for the values. As such, you can form the intervals on your own by computing for classes with equal lengths. So you can form intervals wherein the widths are equal, and then you will just get the frequencies for all those intervals. And these are the steps. So we start first by finding the number of classes or the number of intervals in your frequency distribution. Next is to find the length of the class, how long each interval will be. Next, we start forming the classes, the lower and the upper limits for each interval. We get the frequencies and then we present it visually. So in this example, we have 65 payment times in terms of days. So 22 here means that one element is 22 days. One element paid after 22 days, another one paid after 19 days, and so on. Now, we know that there is no standard way of categorizing payment times, so we can form intervals here with equal lengths. So again, the first step is to find the number of classes, and to get the number of classes, we base it on this equation, 2 raised to k greater than n. So our goal is to look for the smallest integer k that will satisfy this equation, where n refers to the number of measurements in the dataset. So in the example shown earlier, n is equal to 65. So our goal is to look for the smallest integer k that will satisfy the equation. So you can start with k equal to 1 and then keep on increasing until you satisfy this equation. So here in this example, we can start with k equal to 6, where 2 raised to 6 is equal to 64. Now, although 64 is very close to n equal to 65, this is still less than 65. That's why we still have to increase that by 1. So 2 raised to 7 is now 128 and is greater than n. So a better value for k is 7, or there should be 7 classes or 7 intervals in our frequency distribution. Now, you can also use a mathematical approach here, which is to compute for the logarithm of n with base 2, and then that will be equal to k. If the value you will get when using that equation is not an integer, then you have to round it up. So you always round it up to the next integer, and that will be the correct value for k. So in this example, if you compute for the logarithm of 65 base 2, the value you will get is around 6.022. Therefore, if you round it up to the next integer, the value for k should also be 7. So again, using any of those two approaches, you should have 7 intervals for your frequency distribution. The next step is to compute for the class length. And this is based on this formula. First, we compute for the difference between the largest measurement and the smallest measurement and divide that by the number of classes that was determined in the previous step. And in order to get the exact value of the class length, we round it up to the precision of the measurement. So we looked at the data set, look for the most precise number in terms of the number of decimal places, and that will be the basis for the number of decimal places also for the class length. So in the same example, the largest measurement was 29, the smallest was 10, and the number of classes was 7. So computing for the class length, you will get 2.7143, but we round it up to 3 because all the numbers in the dataset were integers. That's why the correct class length that will be used should be 3. But for example, if the dataset has at least one measurement with a number at the 10th place, for example, we have a value here, 21, with a digit at the 10th place, which is 1. Let's say we have one number which is equal to 21.1. Therefore, the most precise number has a digit at the 10th place. We have to round up the class length to the 10th place as well. So in this case, although the number next to 7 is just 1, we round it up, so it should be 2.8. Or if your dataset has 21.12, then the most precise number is up to the hundredths place. Therefore, they should be rounded up to 2.72. So we just round up the class length based on the most precise number in the dataset. Now, step 3 is to form the non-overlapping classes. So, we start the class with the lowest value, and the upper limit of the first class will be the lower limit plus the value of the class length. So, the lowest number is 10. Therefore, the upper limit of the first class will be just 10 plus the class length of 3, or 13. So the first interval will be from 10 to 13, while the next interval will follow a similar approach. So the lower limit of the next class will be equal to the upper limit of the previous class, which is 13, and the upper limit of the next class will be 13, the lower limit, plus class length as well. So that will be 13 to 16. And then keep on doing that until you're able to cover all the 7 intervals that you need to construct. So here, in this example, we will have the following intervals. So that's 10 to 13, 13 to 16, 16 to 19, up to the 7th interval, which is 29 to 31. And to make the classes non-overlapping, we do not include the upper limit in every interval. So the upper limit is not counted. Instead, it will be included in the succeeding interval. So if you have a measurement in the dataset whose value is equal to 13, the frequency should not be counted in the first class, but should be counted in the second class. So if you try to get the frequency for all the measurements in the dataset, again, there were 65. You can do that manually by making the tallies for all the measurements. You can do that for the first 4. Or you can just continue for the rest of the entire dataset, and you'll get the following frequencies. So you have 3 numbers between 10 and 13, 14 measurements between 13 to 16, and so on. And if you add all these values, that will be equal to 65. And then finally, you can present that visually in the form of a histogram. A histogram is basically just a bar chart, but we call that a histogram because the variable in the x-axis is now a quantitative variable. So unlike the example earlier, where the variable put on the x-axis was a qualitative variable, here the variable is quantitative. That's why instead of calling that a bar chart, we now call that a histogram. And on the y-axis, you can also put either the frequency or the relative or the percent frequency. And as you can see here, whether you use the frequency or relative or percent frequency, the shape of the histogram will be the same. So you can, again, these are just 2 styles in creating the same histogram. So there are lots of options for you to choose from, and we just choose the most appropriate style based on what we want to present. One of the aspects that we look at when interpreting or understanding histograms is the shape of the distribution of the histogram itself. And here are some of the common shapes of different histograms. Some histograms are skewed to the right or right skewed when the right tail of the histogram is longer than the left tail, while some histograms have longer left tails compared to the right tail, and we call them skewed to the left or left skewed. Now, some histograms also have equal lengths, so the right and the left tails appear to be mirror images of each other, so now instead we call them symmetrical. So here is an example of a histogram whose shape is right skewed. So this is called right skewed because the right tail, so from the peak to the rightmost value, that's the right tail, is longer compared to the left tail. That's why this is called right skewed. And to interpret a right skewed distribution, we look at the frequencies. As we can see here, you only have fewer frequencies here for the higher values of the quantitative variable payment time, and most of the values are occurring, or the frequencies are mostly in the lower values of x. So because of the lower frequencies for the higher values of x, we have this kind of shape. The skewness is also usually affected by the presence of extreme values. So in this example, you have one measurement whose value is equal to 30, and although the value only has a frequency of 1, it made the right tail significantly longer compared to the left tail. That's why the graph became right skew. This is an example of a left skew distribution wherein the left tail is now longer as compared to the right tail. And again, this happens because most of the frequencies, okay, or most of the values of the quantitative variable are occurring for the bigger values of the quantitative variable. And you only have fewer frequencies for these lower values of the quantitative variable. So it's the opposite of the first example. So this is again affected by the presence of extreme outliers, specifically extremely low values. So this one, 20, is very low compared to the most frequent bottle design rating, which is 32. That's why the length of the left tail is longer compared to the length of the right tail. So again, this is what we call a left skewed distribution. This is an example of a symmetric distribution wherein we can see that the length of the left tail is similar to the length of the right tail. So although they're not exactly similar in terms of percent frequency, the lengths are almost equal or are equal. This is still considered as a symmetric distribution. So it means that most of the values are here at the center, and as you move away from the center, the frequency also decreases. Another common way to present a quantitative variable visually is through frequency polygons. Now, this is also commonly known as a line graph or a line chart, wherein we put a dot or a point above the value of the quantitative variable in terms of also presenting the frequency for that specific value of x. So this is useful when you are comparing two or more distributions because you can put the lines in the same plane. So here we just have one line chart or one frequency polygon for one data set. And if you want to compare this to another similar data set, for example, frequency polygon for exam 2, we can just put another line on the same plane in order to make the comparison easier between the two data sets. So here, this is known as a frequency polygon because the dots or the lines are connected back to the x-axis, forming a polygon with the x-axis. So you can just remove this connection and you will just have the basic line chart that you are familiar with. Now, aside from the relative and the percent frequencies that we have added to your basic frequency distribution, we can also add cumulative distributions or running totals of each interval or each class. So in the previous example, we had these classes and their frequencies, and we can compute for their cumulative distributions. We have the cumulative frequency, cumulative relative frequency, and the cumulative percent frequency. For cumulative distributions, again, we just keep on adding for the next class. So the frequency for the first class is 3. The frequency for the second class is 14. So the cumulative frequency as of the second class will now be 3 plus 14 or 17. And the cumulative frequency for the third class will be, again, a running total as of the third class. So that's 3 plus 14 plus 23 or 17 plus 23, which is now equal to 40. And if you keep on doing that until you've covered all the intervals, you'll end up with the value of n or the number of measurements in the dataset. Similarly, for cumulative relative and cumulative percent frequency, we just keep on adding the relative and the percent frequencies until we cover all the classes wherein the last value should be 1 or 100%. So, in order to interpret cumulative distributions, we don't interpret that based on that specific interval only, but we interpret uh, starting from the lowest value. So, for example, 60 here is a cumulative frequency for the interval 22 to 25. It means that there are 60 measurements between 10 to 25. So it does not apply to just this interval 22 to 25. That applies to the lowest up to that point. Now, in terms of cumulative relative or cumulative percent frequency, we also have a similar interpretation. We do not interpret 80% as the frequency between 19 to 22, but the frequency or the proportion of measurements from the lowest up to that point. So between 10 and 22, it already covers 80% of the measurements. So we can also interpret this in order to identify how the distribution looks like. So there are 7 intervals only, but if you get even just the first 4 classes, that already represents 80% of the entire dataset. While if you look at just the first 3, it already represents 61.54%. It means that more than half of the frequencies are already covered by the first 3, while the last 4, okay, are now just less than 40% of all the frequencies, which means that most of the values are occurring for the lower values of the quantitative variable, signifying that the graph is skewed to the right. And as we have seen earlier, we have seen in the graphs earlier that they really are skewed to the right. Okay, so this is the graph of the dataset, and again, you can see here that the values are occurring more at the lower values of x. Therefore, the graph becomes skewed to the right. Now, if you want to present visually the cumulative distribution, we call that graph an ogive. So whether you use a histogram or a frequency polygon, if the values being presented are cumulative distributions, we call them ogives. And here we plot the point above each upper class boundary of each interval. So the frequency is put at the upper limit of each interval, and then you can connect them with line segments, and again you can use other cumulative distributions. So instead of just the cumulative frequency, you can use cumulative relative or cumulative percent frequencies. So this is an example of an ogive. So for the same data set, the frequency is put here for the interval 10 to 13 on top of the upper limit, which is 13. And then the cumulative percent frequency for the second interval is put on top of the upper limit of the second interval, which is at 16. And as you can see here, it keeps on increasing up to 100%, because again, this is a cumulative distribution, so expect that it will always keep on increasing until you've covered all the numbers in the dataset. Now, another commonly used chart is called the Pareto chart, and this is just a combination of 2 different charts. So, a Pareto chart is a combination of an ogive and a bar chart. So, on the x-axis, you can see here the different types of defects, and these are arranged in descending order. And on the same plane, but using a different scale, we will also put on the same chart the ogive. So it's a combination of the frequencies of the types of defects in their cumulative distributions. And a Pareto chart is normally used in order to see which ones are the can be considered as the critical few. Okay, so there are among the different types of defects, some are critical, some are trivial, and we can look for which ones will be critical based on the frequency and the cumulative percent. So looking at the cumulative percent, we can see that 58.3% is already represented just by the first two, which means that the first two types of defects already accounts for more than half of all the frequencies being encountered in the manufacturing process. As such, according to the Pareto chart, if you eliminate those types of defects, the first two types that accounts for more than half being reduced in the manufacturing. So if you effectively remove those two types of defects, we will be able to see more than half of the previous defects encountered in the past to be reduced. So we will be able to eliminate more than half of the defects that we've encountered in the past. So a Pareto chart is used again normally in order to identify the priority. So ideally, we want to fix all these sources of the defects, but if the resources are limited, we only focus on the critical few. So we focus on the first two in order to eliminate the more than half of the defects encountered, and then after that we can focus on the next type of defects that will be critical again. A dot plot is also another way for us to present a quantitative variable visually. However, this is relatively less common as compared to the histograms. So in a dot plot, we just have one axis which contains the values of your quantitative variable, and then we have dots on top of those different values of x. So the dots here represent the frequency for each value. So if there is one dot above a certain point along the x-axis, it means that there is one measurement in the dataset whose value is equal to that specific point along the x-axis. So here, one dot above 60 means that there is one score for exam 1 that's equal to 60, and two dots here above 90 means that there are two scores whose values are equal to 90 from the first exam. Here's another example of a dot plot, but this is for a different data set. This is for exam 2, and we can see here that again the dots or the frequencies are spread across the different values of the quantitative variable. And when looking at dot plots, we normally look at the endpoints in order to see if there are outliers or measurements whose values are very far from the other values. So here in exam 1, we can see that the lowest score is around 32, while the highest is around 98. While for exam 2, the lowest is around 54, while the highest is 99. So we can see the overall distribution of the dataset through a dot plot as well. And here we can see that it's more scattered, unlike this one. And then here, most of the scores are between 60 to 70 and around 90, while for exam 2, the scores are all within this area, are relatively near this area between 70 to 90. So this is normally just used for moderately sized data sets only. If the data set has too many measurements, for example, if you have 50 more than 50 measurements, then it might be ideal to use something else because the dot plot will just have too many dots and it might not be efficient in presenting your information. Another way to present quantitative variables visually is through a stem and leaf display. In a stem and leaf display, basically what happens is that we are dividing each measurement into a stem and into a leaf, wherein the measurements who have similar stems will be summarized or will be combined into just one stem, and then the leaves will be put on that same stem. So again, we split each measurement to stems and leaves, and then we combine all those with similar stems, and then we put their respective leaves on that row. So this allows us to see the overall pattern of the data. You can see variation, amount of data, and distribution within each class. And similar to dot plots, this is best for small to moderately sized data distributions only. In this example, we can see some measurements whose values are up to the 10th place. So we have here digits at the 10th place. So in order to present this visually using a stem and leaf display, we need first to identify what the stem and leaf units will be. So for the leaf unit, you can start with the leaf unit of 0.1, since the numbers here all have digits at the 10th place. So the 10th place will be the leaf unit. So again, the leaf unit can be 0.1, while the stem unit is always 10 times whatever the leaf unit is. So if the leaf unit used here will be 0.1, it means that the stem unit will be 1. So now, once you've identified what the stem and the leaf units are, the next step is to divide each measurement in terms of a stem and in terms of the leaf. So again, if the leaf unit is 0.1, the leaf for the first measurement will be the digit at the 10th place or at the 0.1 position. So the leaf unit again is 0.1, so the digit at the 10th place is 8. So the leaf for the first measurement will be 8, while the stem is the digit at the 1's place. So here, although the value at the 1's place is just 0, we also include everything else to its left. So the stem for the first number is 30 and its leaf is 8. Now for the second digit, second measurement, which is 31.7, the value at the 10th place is 7, so the leaf of the second measurement will be 7, while the stem will be 31. So in your stem and leaf display later, you will have another stem which is 31, and one of its leaves should be 7. Now in the third measurement, the value is 30.1, so the value at the 10th place is 1. This will be the leaf, while the value to its left is 30, so this will be the stem. Now, since the stem of the third measurement is similar to the stem of the first measurement, we will just combine the two into one row. They will use the same stem of 30, and now the leaves of 30 are 1 and 8. For the fourth measurement, the value is 31.6. So the value at the 10th place is 6. So its leaf will be 6, while the stem will be 31. And again, 31 is already a stem that we identified earlier. So we will combine this leaf to the stem here. So now in your stem and leaf display, so far you have two stems, 30 and 31. For 30, you have leaves 1 and 8. For 31, you have leaves 6 and 7. Now, you keep on doing that for all the measurements in the dataset until you have covered, again, all the measurements. And what you will have is this. So you have a stem and leaf display where in one side, you can see all the stems. And on the right side, you can see all the leaves associated to those stems. So again, we've seen earlier 30.8 and 30.1. So in stem 30, we can see here the leaves. Okay, now the leaves should be arranged in ascending order once you've identified all the leaves, in order to make it easier for us to interpret. So to present a stem and leaf display, we normally put a line to separate the stems and the leaves, and then we include either the stem or the leaf unit or both in order to make it possible for us to interpret the values. So again, in this stem and leaf display, we know that the leaf unit is 0.1 and the stem unit is 1. So to interpret the value of each measurement, we just get the sum product of those values. So the stem unit is 1, leaf unit again is 0.1. So to interpret this, that's 29 times 1 plus 8 times 0.1 or 0.8, giving us a value of 29.8, which means that in the dataset, the lowest value is 29.8, and there's only one measurement whose value is equal to 29.8. In the second row, we have the stem 30. So again, here, a 1 here signifies that there is one measurement whose value is equal to 30.1. But you can also see here that some leaves occur more than once. Specifically here, we have 3/8 for the stem 30, which means that there are 3 values equal to 30.8 in the dataset. So you can even see which one has the highest frequency. Here, among all the values in the stem and leaf display, this one occurs most. So you have 5 consecutive digits with the same value of 4, which means that 31.4 appeared 5 times in the dataset. So if you go back to the dataset, you'll be able to find all those values equal to 31.4. So this is the first, this is the second, this is the third, this is the fourth, and this is the fifth. So that's the most frequent number in the dataset. And again, that was shown here by having similar consecutive values. So a stem and leaf display shows us the distribution. So this is like a horizontal histogram or horizontal bar chart. You can see that it's symmetrical. Most of the values are in the stem 31, and as you move away from 31, the frequencies are decreasing. So the shape is symmetrical. Here's an example of a back-to-back stem and leaf display for the dataset presented earlier about exam scores. So exam 1, you have here the leaves. For exam 2, you have here the leaves, and the stems for both exams are put here at the center. So in order to interpret this, we need to look at the leaf unit, which is now equal to 1, which means that the stem unit is 10 times this leaf unit, or 10. So to interpret this, again, we just get the sum product. So the stem is 3, the leaf is 2. So it means that the value of this measurement is 3 times 10 plus 2 times 1, or 32. So the lowest score in exam 1 is 32, while the highest score in exam 1 is 98. But for exam 2, the lowest score is 55, while the highest score is 99. So now again, the interpretation of the stem and leaf display is quite different because we are now using a different set of stem and leaf units. So here, it allows us to compare two datasets. We can see here, similar to dot plots, that the values or the scores for exam 2 are closer or less varied as compared to the scores for exam 1. So again, a stem and leaf display allows us to visually present quantitative variables, and it allows us to see some distributions of the data sets in order to make certain kinds of conclusions.